All right, sorry for not being here at 1:55. I usually try to get here a little earlier, but it's Friday.
I noticed that and was a tad bit concerned.
Just a tad. Okay, good. But I'm here. So I'm just going to jump into it since it's 2 o'clock. I wanted to show you those websites that I'll have you look at for the midterm again, the CIA World Factbook and the Energy Information Agency, EIA, World Energy Database. So let me stop sharing the PowerPoint, pull up my internet. Is this the one I want? Sure. Okay. So here again is the World Factbook that I flailed on last time. So the way you access information for a country from this is you use this drop-down menu here. Please select a country to view. Let me zoom in on that. So you can drop down here. So let's pick something, France, for example. So we click France, and then we get a map of it, flag, whatever. Here's all the information, some of the information you need. The other information you'll need to get from the EIA. But here's some good overview information. So what exactly are we doing on those websites? You're trying to find data for the Kaya identity. So things like GDP, population, and energy intensity and carbon emissions. So to get some population data, you might click people in society. And so here's the population of France, 67.8 million people. So that's where you'd find some of that information. And then for energy, we have this here. The CIA has a lot of great information about energy, but it's not very well aggregated. So you can't find like total energy production or consumption. So that's where you'd want to go to the EIA, and we'll do that in a sec. But there's a lot of specific data that could be very interesting, you know, later on in the course if you want to do a podcast on a particular nation or something like that. So, you know, like electricity consumption, production, all that sort of stuff. Bunch of fossil fuel information. But here's one key thing that I want you to use in the midterm, and that's how their carbon dioxide emissions. I think this is available on the EIA website as well, but here it's on the CIA website. So this MT, I'll write in the chat. MT stands for metric tons, and the M is, yeah, I guess that's metric tons. And then, so this is 341 million metric tons. And a metric ton is 1,000 kilograms. Not to be confused with a short ton, which equals 2,000 pounds, which is almost 1,000 kilograms, but not quite. It's off by like 200 pounds. Just difference between like American units and the rest of the world. But we'll try to use standard international units in this class, and so that's why it's metric tons. All right, switching over to the EIA here. The way this one works, it starts out with this picture of a map, but then it can get more useful in a second. So you don't have to, you know, have a geography lesson to find a particular country. So if we picked like, I don't know, Ireland, we could click it there. Now we're in Ireland, and you have energy consumption per capita is right here. Energy consumption per GDP, 1.89 thousand BTU per US dollar. Got purchase powering parities. So what does that mean? 1,890 BTUs per dollar. That means in Ireland's economy, to make $1, you have to burn 1,890 BTUs. So that's energy intensity. That's energy per dollar. So you can find it there. A lot more data if you actually click this data button at the top here. And we'll go over this next week too. So don't panic if I'm going too fast. You can click data here, and also, you know, just get BTU is British thermal unit. So BTU is the energy. So that over there was talking about BTU per dollar. So yeah, you can click data here and get all sorts of information. So total energy would be a very useful tab to click here. So total energy consumption, and this is it right here. Consumption in quad BTUs, and this shows it over time. So 0.64 quad BTUs. What the hell is that? So a quad equals quadrillion, and that is 10 to the 15 BTUs. Quadrillion is 10 to the 15. So billion, 10 to the 9, trillion, 10 to the 12, quadrillion, 10 to the 15. But a BTU equals 1,055 joules. This is something we saw in the very first lecture. I don't expect you to remember that. I'm just trying to illustrate what a quad actually means in normal units, non-American units. And so 10 to the 15 times 10 to the 3, 10 to the 3 is 1,000. So a BTU is 1,000 joules. It's actually 1,055, but let's just call it 1,000. So a quadrillion multiplied by 1,000 equals 10 to the 18 joules, which equals 1 exajoule. So that's a number that we're familiar with. That's a number that we know. And this is a societal scale value. The entire world consumes about 550 exajoules over the course of a year, with America consuming 1/4 of that, 125 exajoules. So Ireland's consumption at 0.64 quads is about 1 exajoule, or less than 1% of total world consumption. That makes sense. Ireland's pretty small and it has a low energy intensity. How do you view the light distribution like you showed on Wednesday? That you just, it's NASA, the Earth at night. Type that into Google and there it is. And you can go to nasa.gov. They have a ton of imaging products for that available. I thought they would. earthobservatory.nasa.gov. Yeah, that might be a better. Yeah, the Earth Observatory is where you can get all sorts of imaging products. So here you can get like super high resolution images, which is fun to look at. So this is the Nile in much greater detail than we saw the other day, which is really awesome. Yeah, Tel Aviv is up there. There's Suez Canal. Yeah, this is rad. Okay, let's not get distracted. I'm easily distracted. Okay. So that was just a little bit on those websites. We'll spend more time next week, but that way you can, if you want to start exploring them this weekend, you're welcome to. And yeah. All right, let's get on to lecture. Screen share. Today we're talking about today's energy resources and where they go. So this is total global energy consumption and where it comes from. And then we'll actually talk about those individual resources next week, oil, gas, and eventually renewables and that sort of thing. Okay, get the chat back open. All right, everybody can see the slides? Yeah, okay. So I talked a little bit about how empire basically depends on access to energy. And you can even trace this way back, like some of the biggest empires in Western civilization, Cyprus in 1000 BC, it was all based on burning trees and producing copper during the Bronze Age. Then the Greek and Roman empires, it's awful to say this, but it's in essence, it's a bit of a truth. Their primary energy input was slavery. and those empires expanded so long as they could continue to acquire more and more slaves, both throughout Europe and the entire Mediterranean Sea. And then England is coal, America is oil. Who knows what's next? But yeah, it's been well recognized by leaders the world over that a nation that can't control its energy sources can't control its future. And we're seeing nation states in collapse in present day because of failing energy control. Okay, a couple other things to introduce this lecture with. Right now, our energy supply is a big problem. It's dominated by fossil fuels, and that's wreaking havoc on the environment. Climate change is causing both environmental, species, and societal instabilities. And we need to figure this out because it's only going to get worse. In some senses, I'm a little fatalistic. Like, I feel like the damage is already done, but still, I think we should concentrate all efforts to make the damage less bad, right? Let's make things less worse than exasperate things. So yeah, we can always ameliorate. So I still think there's a lot of I don't know. I think it's still a noble pursuit to try to limit suffering, even though there's suffering already that's baked into the problem. Okay. So if we are to meet the 2C's target, us wealthier, high-emitting individuals, nations, etc., whether in industrial or industrializing nations, will have to accept radical changes to how we live our lives, that or we'll fail on 2C. And this isn't like a call to arms from you or from me per se. It's the wealthiest multinational corporations. Like there's some 50 corporations that are responsible for something like 90% of all emissions. You participate in those corporations when you put gasoline in your car, for example, but it's really these big players that need to make the changes. We shouldn't put it all on the consumer, right? People need to live their lives, and people are dealing with their own extenuating circumstances. But the big levers at the top definitely need to be changed. We'll discuss that, throughout the rest of this class. All right. Where are we at? Right now, it's 2020. This chart was made in 2018 and is about here. We consume about 550 to 600 quadrillion BTUs. Another way of saying that is 500 to 600 exajoules of energy. Because remember, a quad is 10 to the 15, a BTU is 1,000, 10 to the 15 times 1,000 is 10 to the 18, which is exajoules. So we're at about 600 exajoules, and it's thought to continue to grow, if not double from 2000 values by 2050 or so. Why is it going to double? It's because of tremendous economic growth in non-OECD nations. With the advent of globalization in the 90s, and then neoliberal capitalism writ large in the 2000s, many nation states are rapidly economically developing. This is good for human index, quality of life, but it will require much more energy consumption over time. OECD nations are staying relatively flat. So this is places like America, England, France, Germany. And this is largely due to the fact that our populations aren't growing that much. And our energy intensity is going down. The amount of energy required to generate money isn't accelerating that much. Things like efficiency gains, et cetera. But it's definitely growing in non-OECD countries due to population growth and rapid GDP growth. So these nations are becoming more and more wealthy, and quality of life is improving. So that's the big picture. Let's look at it more in depth here. All of these charts I got from the EIA, which is the Energy Information Administration here in America, right in the Smithsonian Mall in DC, and from the IEA, which is an International Energy Agency. It's in Paris, right next to the Eiffel Tower. And then I also used the World Energy Use Outlook, which is from British Petroleum. The oil majors, it's their job, right? They keep track of energy supply and energy flows. And so they have excellent data on world energy use because it directly affects their bottom line. So I definitely use, Exxon and BP both produce excellent documents freely available each year on world energy consumption. I put these two maps here because if you're interested in energy policy going forward, these would be awesome places to spend your late 20s, doing data analysis at one of these locations. I think that'd be a wonderful place to be if you're in your mid to late 20s. Okay. Let's focus on the United States for a second here. Something crazy happened from 2000-ish to 2020. We have this huge increase in energy exports. Anybody know what happened? So we were importing all of this fuel. Then all of a sudden we started making so much that we limited our imports, and now we're actually exporting energy. Fracking, yep, that's exactly what it was. So fracking was an idea that was, we'll talk about it in the gas lecture, but it was an idea that was developed in the 60s, actually, the 1960s, but it required two things. It required economic incentive. There's so much cheap, easily available oil back then that why would you try to get the high hanging fruit? So they just picked the low hanging fruit, which was stuff you could drill straight out of the ground. The other reason is to really get high yields from fracking, you need pretty sophisticated tools. And so now we have like diamond tipped drill bits that are steerable via computers and GPS. And so we can steer the drill and follow the oil reservoir in three-dimensional space, 6 kilometers underneath the ground. And so that was computer technology, GPS technology, and economic incentives really allowed fracking to take off in the 2000s. So that's what happened. And so now we have a lot of energy available to us, for a time. Eventually we'll deplete those reservoirs too. So here's that story in more detail. This is dry natural gas production from oil formations in the United States, in different regions, Southwest, Gulf Coast, and other. And these are projected increases over the next 20 years or so. This is the reference case. Right now we're in this scenario. We're in the low oil price scenario. Why is oil so cheap right now? Any ideas? Supply, yeah, that's a big component, but it's actually the other end of the equation.
No buyers.
Demand. Nobody's going anywhere right now, right? The world's locked down. Some places more than others. And so transportation demand for oil products is way, way, way down. It went so far down. Oil was actually negatively priced in late March. Like you could get a barrel of oil for negative $10. So if you had the warehouse for it, you could get 1,000 barrels of oil, and then you just made $10,000 that day. I don't know what you'd do with that 1,000 barrels of oil though. Probably need a permit for that. Okay. So we're in this scenario here, but the point of this is that we're going to continue to produce a tremendous amount of natural gas due to fracking. Dry natural gas means gas that's produced directly from a reservoir without oil. It's not the gas that's floating on top of a traditional oil reservoir. All right. So here's electricity generation from natural gas and renewables, and it's slated to increase at the cost of coal. So again, this is U.S. centric. We were burning in the year 2000. So just 20 years ago, half of all of our electricity was coming from coal. And that's been supplanted now by natural gas primarily, and then in the later years, these recent years, it's been supplanted by renewables. So coal is going down, renewables and natural gas are growing. So we're shifting from coal to primarily natural gas and then renewables. I'd like to emphasize and promote the shift to renewables. That's something I do in my job versus natural gas for obvious reasons. Okay, so here's just looking at renewable energy generation. Hydroelectricity has been a stalwart for the last 50 years or so. Wind initially grew much faster than solar because it was cheaper, but now solar's gotten very, very cheap ever since 2012, 2013, when we moved from silicon computer chip grade solar panels to much less pure solar panels. So the cost went way down. And so now solar is really taking off and will continue to take off. And that's where the future of renewable energy supply really is. But all kinds are good. This is this is U.S. energy consumption by source over the last, 50 years. And the different lines represent different energy sources. I'm a little color blind, so I have to just use logic to piece this out. Let's start with coal. Coal is this blue line here. And I knew that it's coal because it's going down over time, and that's being replaced by natural gas. I don't know which one's natural gas. I can't see that. If you guys can figure that out, go for it. These two down here, this is gonna be.
It rides the 2 line.
Okay, yeah. So yeah, natural gas is going up, coal is going down. This is petroleum. This fluctuates usually with transportation demand. So it went up until the crash in 2008, and now it's been slowly building again. Probably crashed again now in this year. And then total renewables is this red line. It's just starting to go up in the end here. This was all hydropower, and now it's starting to go up. And then here's nuclear, been increased till about 2000, and then it became prohibitively expensive. It just takes way too much to insure it. I talked to a couple of years ago, I talked to the chief technical officer at at GE, and I asked why you're not building more nuclear plants because there's zero carbon, but you're building all these gas power plants. And he said that for the price of one nuclear plant, we can build like 100 natural gas plants. And if a natural gas plant goes pop, then nobody notices. Where if a nuclear plant goes pop, then we'll have a stock crash. Did nuclear insurance go up after the tsunami in Japan? Yes, absolutely. Yeah, and so what it basically takes is backing from a nation state. And so there's no nuclear plants being built almost anywhere except for China and India, primarily China. There's something like 130 nukes being built in China right now. And that's because it can be backed by the entire nation state of China. It's being built by China for China, not by a corporation like General Electric for a consumer base. Okay, so here's renewable energy production and consumption by source. Wind energy really took off more so than solar, but solar's catching up and will soon pass wind energy. And this is all driven by economics. Check this out, biomass though. Biomass was at parity with hydropower, and now is the greatest source of renewable energy. So what was that? This was like basically wood back here, just burning wood either to generate electricity or directly to generate heat. And then post 2000, it increased due to corn ethanol production in the Midwestern states. And so now we're growing corn to make ethanol to put in our vehicles. When you go to the gas station, it says like, this fuel may contain up to 10% ethanol. It contains exactly 10% ethanol because ethanol is cheaper than oil or cheaper than gasoline, and it's has less energy too. So you won't get as good a gas mileage when you're burning ethanol in your tank than gasoline, than octane. All right, moving on from sources of energy to ultimate sinks. this is another one of those Sankey diagrams where the size of the pipe corresponds to the size of the flow. And so it's I think they're a great illustrative tool, visualization tool. And let's start with electricity generation. So this again is in quads, unfortunately, but just in your brain, translate it to exajoules. So this is all for America. So in 2013, America was consuming 100 exajoules. So again, like about 1/4 of total world demand. And a quarter of that was electricity. And then a third of it is basically electricity. So for buildings, a third of it is transportation, basically. And then the rest of it is stuff. So remember, like, that's what industry basically is. Remember how in your personal energy use, stuff dominated your personal energy use. And that's because there's all these factories making things for you all the time. So that's what's going on there. So to make electricity back in 2013, it was mainly natural gas, and then followed by coal, and then some renewables, and nuclear and hydro definitely dominating those. Okay. And then for transportation, it's all oil. So we take oil, turn it into gasoline, and make our cars run off of it. A little bit of ethanol, that's that stream here from biomass. All right. And yeah, that teeny stream from natural gas, that's for, like, you know, buses that run off natural gas, that sort of stuff. And so all of these energy supplies end up making about 40 exajoules of energy, useful energy, and 60 exajoules of useless energy. What happened? Why did we lose 60% of our energy? Any guesses? Energy conversions. Yes, absolutely. So what happens in an energy conversion? Entropy. Yeah, waste heat. So this is just the second law of thermodynamics. Anytime you change energy from one form, natural gas, to another form like electricity or petroleum to something like motion in a car, you're going to lose a huge percentage of it. So yeah, here it's like 66% of electricity generation gets wasted and 80% of oil gets wasted. And that's just due to poor flows or poor efficiency in conversions. All right, so jumping from 2013 to 2017, I mainly just want to focus on the shift in electricity. So electricity generation, 38.2 exajoules, and it's coming from coal, natural gas, little bit of solar, little bit of wind. When we jump, solar jumps by about 0.5 exajoules, wind jumps by over 1.5 exajoules, coal goes down by 4 exajoules, and gas goes up by 2 exajoules. So coal went down by 4, gas went up by 2, and solar and wind went up by 2. And so this is the shift from natural gas to coal. Man, Stubby's having a good time on the video. Keep it real, man. All right, so now moving on to the sectors of energy consumption. This is an important concept. So usually when we're looking at where the energy goes, we break it into 3 or 4 sectors. The sectors directly follow from your personal energy use. So buildings, so this would be things like lighting, heating and cooling. Transportation, so moving things, cars, trains, planes. And then industry, and that's stuff. Sometimes there's this building sector gets broken into 2 others. So sometimes this gets broken into residential buildings, apartments, houses, and commercial buildings, so restaurants, office space. But in general, there's these 3 sectors: buildings, transportation, industry, and possibly 4 if you have residential, commercial, transportation, industrial. And the reason we break it into these sectors is because it makes it easier to target gains in efficiency and reductions in carbon emissions. So we want to think about how to reduce carbon in transportation. Then we look at, well, what are the fuel sources for transportation? How can we change them? How can we electrify them? How can we reduce the carbon? How can we increase efficiency to reduce overall consumption in that sector? And so usually energy scientists and policymakers kind of focus on one of these three sectors. So in the Bellingham Climate Action Task Force that I participated in the last 2 years, we broke down all of Bellingham's energy consumption into those three sectors and tried to look for carbon reductions in those three sectors. Why did rejected energy increase? Yeah, good question. 21.3, 21.5, 24. It looked like electricity generation got less efficient for some reason. I don't know. Maybe more peaker plants were being used. All right, world energy projections by primary source. So this story is depressing to me. Even though our renewables are expanding rapidly and we're shifting from coal to gas, our total energy consumption is just continuing to grow rapidly. And it's mainly due to developing nations increasing their quality of life and due to population growth. And so even though we're doing our best to switch to renewables, the amount of coal, oil, and gas we're going to consume in the next 50 years just continues to go up. And so we need to make some serious changes. Otherwise, this business as usual scenario is not going to work well. Okay. Today, oil liquids constitute 34% of primary energy supply. This is thought to go down to 28% by 2040, but this is one of those situations where percent signs are deceiving. Politicians always use percent signs because you can hide a lot. What's actually happening is, yes, the percentage of oil is going to go down, but the overall total consumption of oil is going to go up tremendously, from 50 quads to 62 quads. Today, coal is still 28% of primary supply. So again, we're just completely dominated by fossil fuels, oil primarily at 34%, coal at 28%. US coal consumption is going down, but it's increasing elsewhere in the world. And yeah, so just talking about energy supply here, oil, coal, and then finally gas is the other big component. All right. And so coal demand is decreasing in Europe and the United States and these OECD nations, but it rapidly increased in China due to their economic revolution in the last 20 years. And then it's going to increase in India with their economic revolution over the next 10, 20 years. And then sub-Saharan Africa constitutes this other big growth in coal in this location here. Natural gas, 22% of primary supply. This is going to increase over the next 20 years as coal goes down and natural gas increases. And that growth will again concentrate in both OECD, but primarily in non-OECD nation states. So projected growth in natural gas is 70%. It's just the next fuel transition. We went from wood to coal, coal to oil. Now we're going from oil to natural gas. And there's a lot of it. So we'll have a whole lecture on natural gas. What does that percent of primary supply number mean? It means the percentage of total world energy consumption. So that means that of all the energy that powers the entire society, global society, 22% of that comes from natural gas, 28% of it comes from coal, and 34% of it comes from oil. So yeah, here, there's natural gas everywhere. Even the places where we don't see natural gas, there certainly is natural gas here. South America and Africa used to be the same landmass during Pangea, and so there'd be a lot of natural gas right there. All right, I'm kicking some fools off of this. Okay. World energy consumption rises 28% over the next 30 years or so. And again, this is primarily concentrated in non-OECD nation states, India, China, and sub-Saharan Africa. And that will be supplied, again, by these big three, the big three fossil fuel, petroleum and other liquids, natural gas and coal. Other liquids means non-conventional oil. So oil that you get from fracking or from tar sands, not the light sweet crude that you get from traditional plays in Saudi Arabia or Burkina Faso or Texas, for example. What's OECD? OECD is Organization of Economic Countries Developed. It's a French phrase. That's why country and developed are backwards there. So I think it's like 8 to 20 nation states that are thought to be economically developed, have a high standard of living, and they meet several times a year. Representatives from those nation states meet several times a year in Paris in an effort to concentrate and share their wealth to develop other nation states. It's just a way of classifying countries. In the olden days, based off of GDP per capita. In the olden days, and by agreement too, they have to be democratic states. They can't be dictatorships. In the olden days, you used to say like first world and third world. That's out of favor. But now we say OECD. Okay, so the short of this lecture is that oil, gas, and coal dominate our energy supply today. It will continue to dominate our energy supply in the next 20 years. And this is a severe challenge to maintaining global warming at non-dangerous levels. 2C warming, 2 degrees Celsius warming, is thought to be a dangerous level because it is a temperature in which human evolution did not occur. Basically, if we warm the planet by 2 degrees Celsius from 1960 baseline, we will now be in a planet that humans didn't evolve in. So we will be in a planet that's warmer than it has been in the last 100,000 years. What does that mean? We're not entirely sure. We just know that species, the planet over, evolved for certain conditions, and now we are putting the planet in a different thermodynamic state. It's thought to be not only environmentally rapacious, but also very damaging to world economies, as well as coastlines get swallowed up and crops migrate and grasslands become desert, et cetera, et cetera. We'll talk a lot about this in our climate change lecture. That's just where that 2C comes from. It's a state that human evolution doesn't know. And right now, we've emitted enough carbon to get to 1C. We're already there. We're at like 1.1C. We're 1.5C is basically already baked in. And to avoid 2C, we have to not emit another 1,150 gigatons of carbon over the next 20 years. We've emitted half of that already, and it's projected that we'll easily emit that second half in only 20 to 30 years. Why? Because of exponential growth, right? We're emitting far more carbon this year than we were 10 years ago, and then exponentially more 10 years ago than we were 10 years before that. So it's going to be a challenge. Again, I'm not optimistic, but I'm not cynical. I still think we should do everything we can to make things as less bad as possible. Ways to do it, we can greatly increase energy efficiency, so provide the same energy services but with much less energy. So switching things like a natural gas furnace to an electric heat pump would increase efficiency of your own residential heating by 4x. Make that electricity clean, so switch everything to electricity, stop burning fossil fuels, then make that electricity clean with renewables, stop burning fossil fuels in power plants. And then we could also do CCS, which stands for carbon capture and sequestration. To make this effort worldwide, it's going to cost trillions of dollars, but economists project that if we don't do anything, it's going to cost us tens of trillions of dollars in economic damage. Yeah, well, this is the scary part. We're going to talk about solutions for, the majority.
But if you ask someone at a debate about that,
yeah,
they'll only focus on how much it costs to go to renewables.
Yeah, and that's why it's important to focus on, the cost of doing nothing. And the cost of doing nothing is much more severe. Yeah. Yeah, I can't. There's all sorts of analogies I could come up off the top of my head, like, your house is on fire and you can turn on a hose and start spraying it, and you're like, but wait, I'll have to pay for some water if I do that. Well, if you don't do anything, you're going to pay a lot more money when your house burns down. I don't think it's that dire, but I'm just trying to use, how much energy does it take to make solar panels? I don't know that off the top of my head, but I know their energy return is 18 to 1. So you spend 1 unit of energy building a solar panel, put that solar panel up, over the next 20 years, it will give you 18 units of energy back. So it pays for itself. It pays for itself in 1.5 years. Wind pays for itself in 3 months. The amount of energy you get back from wind is like 80 to 1. So yeah, we'll have a lecture on net energy analysis towards the end of the class. All right, so we got about 7 minutes left. I'm going to talk for about 3 minutes and then just try to field some questions because we did so much, so many charts in this lecture. Let's just go to this one. So what can we do about this 2C problem? How can we limit carbon emissions? Well, we use the Kaya identity again. These are our tools. We can lower population. Again, that's a bad look unless we do things like women's education. We can lower GDP. That's usually untenable too in capitalistic societies. Telling the society that they'll make less money next year than they did this year is not a winning argument. It's not going to work for capitalistic and democratic societies. But the other thing we can do is lower our energy intensity. So can we make more money using less energy? So let's look at these individual levers. Here's population. OECD nations are flattening out, on average, like 1.7 children per family or so. Some nations are even sub 1. A lot of Scandinavian nations are now sub 1. But non-OECD nation states, the population is still increasing rapidly. And this is how it was in a lot of places before development. And that's just because life was harder, and people would have more children because it wasn't a guarantee that they'd live to adulthood. And then the primary reason is poor access to birth control, family planning, women's education. So when women are able to control their fate, then populations stabilize rapidly. Another level we can control is gross domestic product. So the wealth of nations. This is thought to increase both in OECD and non-OECD nations. So this is going to increase energy demands and commensurate carbon emissions. But the energy intensity is thought to go way down as economies shift from resource extractive economies, so mining for iron and coal and these sorts of things, to service-based economies where we exchange ideas and information, and that's how people make money. Finally, carbon intensity is thought to go down as we shift from coal to gas and gas to renewables. And so hopefully that's a good good highlight to the story. But because these things are going up so rapidly, they may dominate this. And even though carbon intensity is going down, recall carbon intensity is metric tons of CO2 per energy unit. So in this case, it's billion BTUs. If the per billion BTU, if the total number of BTUs is going up, even if the carbon intensity is going down, we'll still be emitting more and more carbon just because we're burning more and more energy. And so this is where energy efficiency becomes really important. Can we provide more and more energy services without as much carbon? Okay. Shifting to renewables, blah, blah, blah. Finally, I'll conclude with these energy transitions take about 70 years. I want us to be cognizant and forward-looking and make this next transition much, much shorter from gas to renewables. I replotted that graph that I showed last time in perhaps a more visually digestible way. This shows energy transitions for the last 200 years or so. And this is percent share of energy supply for all of the world. In 1850, it was 92% wood. That was the primary energy supply for everything. And that shifted to coal. And by 1910, 1920, it was completely dominated by coal. Oil was discovered in 1857, around here or so, started to become more and more useful. And then it wasn't until post-World War II that oil dominated now over coal. And then now gas is beginning to rise in a fraction of total energy consumption. Nuclear is here, and now renewables are just starting to peak. So what I want is renewables to grow and cover up this whole plot here. And hopefully we do that sooner than later. All right, questions?
So plan for next week. What do we need to do to prepare for Monday?
Not much of anything. You can have a look at those two websites, CIA, EIA, to reduce your time using them for the midterm. Have a look at these three equations that I'm just going to write qualitatively. So power equals energy over time. Heat capacity, so delta E equals mass times heat capacity times change in temperature. And is there a study guide for the midterm? No, I think I posted useful equations already on Canvas though. I think, yeah, I did. That's in the logistics sentence. There's a list of useful equations. And again, the midterms, open book, open notes. Kaya identity question would be like, what would be the energy intensity of France or something like that in terms of dollars per joule? So you'd plug in their total energy consumption, their population, their GDP per capita, and you get something like that. Third equation is efficiency. So efficiency equals get over pay. And that you have to have the energy units be the same both on the top and the bottom. So like joules over joules, etc. Kilowatt hours over kilowatt hours. And then, yeah, Kaya identity would be the last one. Open book, open notes. We have a week so we can talk about it. I'll release it Sunday. We can talk about it Monday and Wednesday. It's not scary. This is an Energy 101 GUR class. So we'll all get through it together.
All right, thank you.
Yep. Yeah, links to the website are posted in two places. It's posted in an announcement that I made, and I'll post it on the midterm itself.
Thank you. Have a nice weekend.
Yeah. What time on Friday is it due? Yeah, I'm not sure yet. Yeah, have a nice weekend. Sorry about all the crazy distractions and lecture. People should let me know that's going on. Unless you enjoy it, then just let it ride. Yeah.
So should we know most of the trends on these graphs for the midterm?
No, this is just broad qualitative strokes that I wanted you to understand where society gets its energy today, and it gets it from oil, coal, and gas. And it's looking like it's going to be oil, coal, and gas going forward unless we do something.
Okay.
This is just setting up the problem that in the rest of the class we'll think about solutions to this problem. Good question.
All right. Thank you, Charlie. I'm gonna head out.
Sounds good. See you, Cody. Have a good weekend.
You as well.
All right, I'll hang out for another 20 seconds or so. Anything else? You're very welcome. Adios. All right, see y'all. Have a good weekend.